In this section, we're going to go over some hypothesis testing when sigma is known, or when our population standard deviation is known. And just a warning here, this video is probably going to be pretty lengthy, so what I would suggest is actually take a couple breaks and then come back when you're ready. Okay, so before I begin this section, I want us to remember what we did in chapter 7. So here, recall from chapter 7, and if you remember, the whole theme about chapter 7 was confident interval. And depending on which information you were given, you use different methods to compute some of these confidence intervals. For example, we learned how to compute confidence intervals when our population standard deviation sigma is known, right? This is also called the Z method. Z method. So that's one way. But what happens when you're not given the population standard deviation, when you don't know what that value is? So then we learn how to find confident interval when sigma, or our standard population standard deviation, is unknown. And the way we did this is that we replace our population standard deviation sigma with S. And here S is just the sample standard deviation, right? And we were able to compute this because we already had a lot of practice of computing sample standard deviation. If you remember, S was just equal to the square root of summation of x sub I minus x bar squared divided by n minus 1. And this was from section 3.2, just a refresher. And this is when we were doing the Both method to kind of organize our data. So that's how we already computed sample standard deviation. So it's nothing new for us. So anyways, when we were computing these confidence intervals, when our sigma is unknown, this is often called the T method. T method. And we use something called the student T distribution. Again, this is just all reminders. Student T distribution, right? And this is when we had to compute the degrees of freedom and use a different chart. Okay, so this is one method. This is another method. And another thing we learn about is computing confidence intervals. For proportion, for population proportion P. And here we were able to use our sample statistics P hat, or in other words, our sample proportion. And this follows, this kind of follows the same rule with Z method here. So remember, this is just a reminder. This is all from chapter 7. When standard deviation is known, when it's unknown, and for proportion P. Why am I telling you guys this, or why am I reminding you of this? It's because hypothesis testing is kind of exactly the same thing. We're going to have hypothesis testing, how to compute hypothesis testing when standard deviation is known, how to compute hypothesis testing when standard deviation is unknown, and how to compute hypothesis testing when dealing with proportion. So here, this is just a little bit of a foreshadow Right now in this section, 8.2, we're going to deal with hypothesis testing when sigma is unknown. Sigma is known. Then later in 8.3, we're going to deal with hypothesis testing when sigma is unknown. And finally, in section 8.4, we're going to talk about hypothesis testing dealing with proportion. So just a little overview of what we're going to do throughout chapter 8. Okay, so now let's get started with this section. Okay, so section 8.2, hypothesis testing when for mu when sigma, or our population standard deviation, is known. So there's two ways to perform hypothesis testing. One, it's called the critical value method, and the other is called the p-value method. So right now, first we're going to talk about the critical value method, and then later in the notes, we're going to talk about the p-value method. So first, to compute the critical value method, we need to know something called a test statistic. So here, the whole idea, or the critical value method, is based on the idea that we should reject our null hypothesis. Remember, this was H0 just represent our null hypothesis, and this was from the previous section, 8.1. So here the idea is that we should reject H0 if the value of the test statistic is unusual when we assume our null hypothesis to be true. So when performing statistical tests, we need to have a sample statistics. And usually this is just x bar or p hat to compare to the value in the null hypothesis. Okay, so some important definition. So what exactly is a test statistics? So here, in the case when sigma is known, the test statistic is the z-score of the sample mean x bar. So here, the test statistic is just going to be x bar, which is the sample mean, minus mu naught, which is the value of our null hypothesis, over sigma over square root of n. And if you remember, this value underneath kind of looks familiar, and it should. It's something we've seen before. This is the same as the standard deviation of our sample mean distribution. So this is just sigma over square root of n. So if you like, if it makes it a little bit easier, you could rewrite this test statistic to z is equal to x bar minus mu naught divided by sigma x bar. Or if this kind of confuses you a little bit, you can also just stick with this and just plug in the values and then put it in your calculator. Whatever helps you the most. Okay, so we're going to do a couple examples of actually how to compute our test statistic. So example 1. A test is made of our null hypothesis is mu equals 50 versus our alternative hypothesis mu is greater than 50. We have a sample size n of 75 is drawn, and x bar is 56. The population standard deviation sigma is equal to 20. We want to compute the value of the test statistic z. And again, this is just the first part, the beginning of actually computing hypothesis testing. So let's do some practice. So here we already know what our hypothesis testing are. Here we have our null hypothesis, mu is equal to 50, versus our alternative hypothesis, mu is greater than 50. So we can just write it right here. Mu is equal to 50, and h1 is mu is greater than 50. So this is in the form of h naught mu is equal to mu naught, and h1 is mu is greater than mu naught. So here, our mu naught is just going to be, it's always going to be the value of what we're testing. Here is 50. So let me put this in red. We have mu naught is equal to 50. That's what we got here because we're dealing with 50. And then we have our sample size, n, is equal to 75. Because here it tells us that the sample size, n, is 75. And it also tells us the sample mean is 56. So x bar is equal to 56. It even gives you the population standard deviation, sigma, which is 20. So sigma is equal to 20. Now that we have all of our values, we could actually compute our test statistic. So z, I'm going to write it in blue, z is equal to x bar minus mu naught divided by sigma over square root of n. And if you want to compute this first and then plug it in, you could do that, or you could just put it all the values at once and just put it in your calculator and get your value. It's totally up to you. So what I'm going to do is just input all the values and just put it in my calculator. So this is going to be 56 because 56 is our sample mean, minus mu naught, which is 50 because that's what we're testing, divided by 20 over square root of n. Oh, sorry, square root of 75 because 75 is our sample size and 20 is our sigma. And if you put this in your calculator, this is going to be 2.5981. And what I like to do is round this to 2 decimal places. So what we have to do is look at the value next to it, and if it's greater than 5, we round up. So this is going to be 2.60. So we just calculated our test statistic. So z is equal to 2.60. And you're probably asking, why do we round it up to 2 decimal places? Well, we're actually going to need that in later into the notes, but we'll get into that. Okay, how about this example? Here we have a test of h naught is when mu is equal to 14, and our alternative hypothesis h1 when mu is not equal to 14. And we have a sample size of n equals 48. Our sample mean is 12, and the standard deviation of 6. And again, we want to compute the value of our test statistic z. So first, I'll write down our tests. So our null hypothesis will be mu is equal to 14, and our alternative hypothesis, h1, is mu is not equal to 14. Oh, just a reminder. Since our alternative hypothesis is mu is greater than 50, what kind of test is this? Is this left tail, right tail, or two tail? If you remember from section 5.1, let me write this in purple or in green. Because the arrow is kind of pointing to the right, this kind of gives you an idea that we're dealing with a right tail test. Okay, so for here, since we're dealing with not equal to 14, not equal to 14, what kind of test are we dealing with? A right tail test, a left tail test, or a two tail test? Well, since it's not equal to 14, we know that this is going to be a two tail test. Two tail test. Awesome. And this test here is in the form of H0 is mu is equal to mu naught, and H1 will be mu is not equal to mu naught. So here again, our mu naught is just going to be the value of what we're testing with, which in this case is 14. So here, mu naught, mu naught is 14. And we know that our sample size is 48. And our x bar, or our sample mean, is 12, and our population standard deviation is 6. Now that we have all of our values, we can compute the test statistic, z. Let me write this in blue. So z is going to be x bar minus mu naught divided by sigma over square root of n. So if you put all the values in, this is going to be 12 minus 14 divided by 6 over square root of 48. And this is going to be equal to negative 2.3094. Or if you round to two decimal places, it's going to be negative 2.31. Awesome. Okay, last one. So let's say we have this test here. Mu is equal to 5 versus mu is less than 5. And we have a sample size of n equals 87. And we have a sample mean of 4.5. And a population standard deviation of 25. We want to compute the test statistic z. So I'm going to write our null hypothesis will be mu is equal to 5. And our alternative hypothesis, H1, will be mu is less than 5. Okay, so in green, what kind of tests are we dealing with? Are we dealing with a left tail, a right tail, or a two tail? Well, since this arrow, the way I like to think about it is, since this looks like an arrow pointing to the left, we know that this is going to give a left tail test. Okay. So here in our test, this is in the form of H naught will be mu is equal to mu naught, and H1 is mu is less than mu naught. So here our mu naught is, you get it? You gets it, it's 5. It's whatever value we're dealing with in our testing. So here was 50. In this example, it was 14. So now in this example, it's 5. So I'll put this in red. Mu naught is equal to 5. We know that our sample size, n, is equal to 87. Our sample mean, x bar, is equal to 4.5. Our population standard deviation, sigma, is 25. Now that we have all of our values, we could again compute the test statistic. I'm gonna write that in blue. here z is equal to x bar minus mu naught divided by sigma over square root of n. So if you plug all the values in, this will be 4.5 minus 5 all over 25 divided by square root of 87. If you put this in your calculator, this should be equal to negative 0.1865. But if you want to round this to 2 decimal places, we look at the number next to it. If it's greater than 5, we round up. So that's why this is going to be equal to negative 0.19. Okay, so now we had a lot of practice of computing our test statistic. Again, this is not this is only the first part of computing hypothesis testing. We still need to do a couple more things. Okay, so before I move on, let me just box all of the answers. So here we had z, our test statistic, equal to negative 2.31. Oops. And here we have z is equal to negative 0.19. Okay. Next, we're going to talk about something called the critical value and how to attain the critical region, and something called a significant level. Okay, so a couple important definitions. The critical value forms the boundaries between the values that are considered unusual and the values that are not. The region that contains the unusual value is called the critical region. So these two kind of go hand in hand. The critical value is the boundary between the values that consider unusual values and are not, but then the critical region is just the region where it's considered unusual. Okay, and then there's two definitions of significant levels. They're both saying the same thing, but in a different way. So number one is that the probability that we use to determine whether an event is unusual is called the significant level of the test. And this is denoted by the letter alpha. And again, this is just a Greek letter. So if you want to write it, imagine like an infinity sign, but kind of like, actually, yeah, a little bit of it off. So it kind of looks like this. So alpha, the way I write it is just like that. So this is it's a Greek letter, alpha. Okay. Another definition is that the significant level alpha is just the area of the critical region. And depending on which test are we dealing with, either a left tail, right tail, or two-tail, your critical region and critical value might be different, or it is different. So here's a way to kind of visualize it. So let's look at a left tail test. Okay, so a left tail test is when our alternative hypothesis mu is less than some value mu naught. We have a critical value such that the area to the left of that critical value is going to be the area of our significant level alpha. So let me just write a couple things down. Hold on. For left tail so for a left tail test, the critical value is negative z of alpha. So this is going to be our critical value, which has area alpha, whatever alpha is, to its left. And one thing you want to know is that to reject our null hypothesis H naught if our test statistic is less than or equal to our critical value, negative z sub alpha. And again, this is just only dealing with a left tail test. And we're going to do a couple examples on this in a little bit. Okay, so now let's deal with what happens when you're dealing with a right tail test. So let me just draw a line. Okay, so for right tail test, the critical value, we're going to call it positive z of alpha. So this is our critical value for right tail test, which has area alpha, whatever alpha is, it's a number, to its right. And here we reject our null hypothesis H sub 0 if our test statistic is greater than or equal to our critical value z of alpha. And again, this is just dealing with if we know if we're dealing with a right tail test. And this is what a right tail test is. It's mu is greater than some value, mu sum naught. Okay, what about when we're dealing with two-tail tests? And you know when it's a two-tail test, when mu is not equal to some value, mu sum naught, or mu 0. So this is our alternative hypothesis. So actually, our critical values will be in the location where if we take the area to the left and the area to the right of these two values, if you add them up, they're going to be equal to alpha, where again alpha is just our significant level. So let me just write a couple things down. For two-tailed, the critical value z of alpha over 2 which has area alpha over 2 to its right, and negative z of alpha over 2, which has area alpha over 2 to its left. So when we're dealing with two-tailed tests, we actually have two critical values, negative z of alpha over 2 and positive z of alpha over 2. Oops. Awesome. And one important thing you have to remember is that we reject our null hypothesis, H sub 0, if our test statistic, z, is greater than or equal to z of alpha over 2, or our test statistic z is less than or equal to negative z of alpha over 2. And you're probably asking yourself, how do I get this value? How do I actually compute these critical value, z of alpha over 2, z of alpha, negative z of alpha? How do I actually get these values? And that's actually a good question. So there's a couple of ways you could do it. You could use technology. You could buy a really fancy calculator and it'll give you the answer. Or you could just follow this chart, because I don't want you guys to actually go and buy a very fancy calculator. So if we actually use this chart, we could compute or find out what our critical values are, depending on which test we're dealing with, either a left tail test, a right tail test, or a two tail test. So we're going to do some examples of how to find these critical values. Okay, so example 1. Find the critical region and critical value for a left tail test when we have a significant level alpha of 0.05. So what is this asking me to find? Well, since we're dealing with a left tail test here, we're going to need to find our critical value, negative z of alpha. So here, what we're trying to find let me just draw this real quick. So our standard normal curve with a mean of 0, we need to find this critical value, negative z of alpha, where the area to the left is our alpha, and the critical region is just all this stuff. It's all the values to the left of our critical value, negative z of alpha. So how do I find this value here? How do I find negative z of alpha, or our critical value? Critical value for a left tail test. So since we know our significant level, 0.05, we could rewrite this as negative z of 0.05. Oops. Now we are able to use the chart, which is right here. So here in our significant level, we want to identify which one are we working with. Since the problem is asking you for alpha equals 0.05, we look at 0.05, which is right here. Oops. But are we dealing with a left tail test, a right tail test, or a two tail test? Here we know that we're working with a left tail test. So here it is. So where they intersect is what our critical value is. So, and notice that there's a negative here, which kind of gives you more confident that this is our value, because there's a negative here. So this is going to be equal to negative 1.645. So our critical value for the left tail test when alpha is equal to 0.05 is negative 1.645. And we got this value again from the chart. Okay. How about this one? Find the critical region and critical value, and critical value for a right tail test when we have a significant level of 0.05. Since we're dealing with a right tail test, our critical value, z sub alpha, it's going to look like this. It's going to be positive z of alpha. That's what we're trying to find, which again is just, if we take the area to the right of this value, it's going to be equal to alpha, our significant level. So here, let me just draw this real fast. We have a standard normal curve with mean 0, and we're trying to find this value here, z of alpha, positive z of alpha, where the area, is this. So this has an area of alpha, but it's also our critical region. So let me just mark here. This is also our critical region. Is everything here. Okay, so how do we find this value, z of alpha, positive z of alpha? We want to find this, z of alpha. Since we already know what alpha is 0.05, we could just plug it in. So this is equal to z of 0.05. What we could do is use the chart. Since we're dealing with a significant level of alpha, and alpha is 0.05, we look at this column. All right. And since we're dealing with a right tail test, we go to right tail test and we highlight that row. And where they intersect is what our critical value is for the right tail test. And here is positive 1.645. And that kind of gives you more confidence because our our critical value is positive. So this is going to be equal to 1.645. So this is our critical value for a right tail test when alpha is equal to 0.05. And let me just box this answer too. So here, this was the critical value of our left tail test when alpha is equal to 0.05. Okay. Now let's look at this example. Find a critical region and critical value, sorry about that, for a two-tail test when we have a significant level of 0.05. So what does this mean? Since we're dealing with a two-tail test, we're actually going to find two critical values where the area to the left of this and the area to the right of this value is, if we add them together, it's going to be equal to alpha, or our significant level. So let me just draw this real quick. We're trying to find negative z of alpha over 2, negative z of alpha over 2, and positive z of alpha over 2. Oops. And here is going to be our critical region. Our critical region will be this part here and this part here. So how do we find these values? How do we find negative z of alpha over 2 and positive z of alpha over 2? So that's what we're trying to find. Negative z of alpha over 2 and positive z of alpha over 2. Where are these going to be? Well, since we know we're dealing with a two-tail test and we know our significant level is 0.05, we could look at the chart. So here we have a significant level of 0.05. And we have a two-tail test. So our critical value would be plus or minus 1.96. And this kind of gives you more confidence because we know we have two critical values and one positive, one negative. And this is it. So here, this will be negative 1.96, and this will be positive 1.96. So let me just box these up. Okay, so now we just did a couple examples, a couple practice how to actually find our critical regions and critical values. Okay, so let me review what we've done so far. We have some practice of computing our test statistic. We have some practice of actually computing our critical values and critical regions. Now we're going to put them together, and that's how we're going to perform hypothesis testing. Okay, so before even thinking about performing hypothesis testing, we need to check again that all the requirements are satisfied. So if one of these does not satisfy, then we cannot perform hypothesis testing when sigma is known. Okay, so the first thing we have to check is that we obtain a simple random sample of size n. Since in this section we are talking about hypothesis testing when sigma is known, or when our population standard deviation is known, we need to know the value of sigma. It should be somewhere in the problem. X, our sample mean distribution, has to be normal, and we could check this by checking one of two things. One, if X already comes from a normal distribution or the population is already approximately normal. If this should say somewhere in the problem. If not, then you could check number two. Is the sample size large enough? Is our sample size greater than 30? If all these requirements are met, then we're able to proceed to do or to perform hypothesis testing. Okay, so here is some of the step for performing hypothesis testing for mu when standard deviation, population standard deviation, is known, and we're doing it using the critical value method. Step one is we have to state the null and alternative hypothesis. The null hypothesis is typically in the form, the null hypothesis is typically in the form of H naught, mu is equal to mu naught, where mu naught is just like a value, it's a number somewhere in the problem. The alternative hypothesis can be stated of one of three ways. We could say that mu is less than mu naught, where again mu naught is just a number. We could say that mu is greater than mu naught, or mu is not equal to mu naught. And this should be all refresher from 8.1. We need to find the critical value corresponding to the desired significant level alpha. And we already did some example of how to do this just a while ago. And then we have to compute our test statistic, z. And then we have to determine whether to reject our null hypothesis, H0. And how do we do this? How do we determine whether to reject our null hypothesis? Well, it kind of depends on what test you're dealing with, a left tail, a right tail, or a two-tail test. If you're dealing with a left tail test, and remember, you know it's left tail when mu is less than some number, mu naught, we reject our null hypothesis if our test statistic is less than or equal to negative z of alpha. And again, this is just the critical values, and we already done some practice how to compute critical values. If you're dealing with a right tail test, and you know if it's a right tail test if mu is greater than mu naught, where again mu naught is just a number. We reject our null hypothesis if our test statistic is greater than or equal to z of alpha. And again, z of alpha is just your critical value. If you're dealing with a two-tailed test, and this is when mu is not equal to mu naught, where again mu naught is just a number, then we reject our null hypothesis if our test statistic z is greater than or equal to z of alpha over 2, or our test statistic z is less than or equal to negative z of alpha over 2. If one of them is true, then we reject our null hypothesis. And this is dealing with a two-tailed test. Finally, step number 5, and probably the most important step, is we have to state our conclusion. We have to interpret our results. It doesn't matter if we're able to compute all this above, if we're not able to actually know what we're dealing with or know what it means. So let's say we reject our null hypothesis. So let's say one of this is true. We reject our null hypothesis. How do we say this? How do we state our conclusion? Well, we could say something like, we have sufficient evidence to conclude and input whatever your alternative hypothesis was. So that's one way. Probably the easiest way. What happens if we fail to reject our null hypothesis? Then we could say that there is not enough evidence to conclude our alternative hypothesis, whatever our alternative hypothesis is. Depending on the problem that we're working with, these are going to be different. Okay, now we could finally perform hypothesis testing when sigma is known via the critical value method. Okay, the American Automobile Association reported that the mean price of a gallon of regular grade gasoline in the city of LA in July 2013 was $4.04. A recently taken simple random sample of 50 gas stations in LA had an average price of $3.99 for a gallon of regular grade gasoline. Assume that the standard deviation of price is 15 cents. So an economist is interested in determining whether the mean price is less than $4.04. We want to use the critical value method to perform a hypothesis test at a significant level of 0.05. So what I like to do first is actually collect all the things that is given to me. Since we know, and this is probably the easiest, that we had a simple random sample of 50, we know that our sample size, n, is equal to 50. We also know that in this simple random sample of 50 gas station, we had an average price of $3.99. Since this was a simple random sample, this average price is our sample mean. So X bar. So $3.99. Cool. We also know that the standard deviation is 15 cents. So our sigma here is 0.15. And we're working with a significant level of alpha equals 0.05. So alpha is equal to 0.05. First, we want to check our requirement. Before we even begin performing hypothesis testing, we have to check if we can actually do it. Notice that our sample size, n, is equal to 50, which is greater than 30. Since it's greater than 30, we know that all the requirements is checked. We also know that it comes from a simple random sample, and we know that our sigma is known. So we're able to continue performing our hypothesis test. Next, we want to establish the null and alternative hypothesis. So here we want to write our null, a sub 0, and this is always going to be mu is equal to something, and our alternative hypothesis, H sub 1. And this is always going to be mu is either less than, greater than, or not equal to some value. So how do we write this? How do we know this? Well, if you look back into the question, we have this person, an economist, is interested in determining whether the mean price is less than $4.04. So he's saying that the mean price of gasoline in LA is less than $4.04. So that means our null hypothesis is that it's going to be equal to $4.04. And let me just write this in green. Since this is less than, what test are we dealing with? A left tail, right tail, or two-tail test? The way I like to think about it is that this kind of looks like an arrow pointing to the left. So this kind of gives you an idea like, oh, we're dealing with a left tail test. Pretty easy to remember. Okay, so we have our null hypothesis and our alternative hypothesis. But what I like to do is I like to write this in words. What does this mean? And you're going to see why in a minute. It's going to make a little bit life a little bit easier. So here, this is saying that the mean price of regular grade gasoline in LA is $4.04. But the alternative hypothesis, this economist, this person is saying that no, the mean price of regular grade gasoline. I misspelled gasoline, huh? In LA is less than $4.04. So that's kind of the argument here. Okay, so now that we wrote down our null and alternative hypothesis, we can continue. Next, we want to find the critical value and the critical region. So since we're dealing with a left tail test, if you remember, let me just draw this real fast. We want to find our critical value, negative z of alpha, where the area to the left of this value is going to be equal to alpha. So in other words, this is going to be our critical region. It's going to be all of this. So how do we find this critical value? So again, this is just our critical value. How do we find this? Well, again, we could use the chart again. So this is negative z. Let me write this in blue. Negative z of alpha. Since we have a significant level of alpha is equal to 0.05, this is going to be negative z of 0.05. What is this going to be equal to? Well, we could use the table again. So if you recall, this table here, let me just erase this real fast. Oops. Let me just erase this real quick. We have a significant level of 0.05, but since we're dealing with a left tail test, we know that our critical value is negative 1.645. Since this is a negative number, that kind of gives you more confidence because we know that it has to be a negative number. So this is going to be equal to negative 0.645. So we just found our critical value and the critical region. So this is, let me just emphasize this. This here value is negative 1.645. Yeah. Okay. Next, we want to actually compute our test statistic, z. So z is equal to x bar minus mu naught all over sigma over square root of n. Since we have x bar and we have mu naught and sigma and n, all we have to do is plug in all the numbers. So this is going to be equal to 3.99 minus 4.04 divided by 0.15 divided by square root of 50. And then if you plug this in your calculator, this is going to be equal to negative 2.3570. And you can round this to 2 decimal places, negative 2.36. So we look at the number next to it and round up. Okay. What is our conclusion? Do we reject our null hypothesis or do we fail to reject our null hypothesis? Well, we want to ask ourselves a question. So question, this is a Q. Is z less than or equal to negative z sub alpha? Question mark. So how do I get this? How did I get this? Well, remember in our step here, since we're dealing with a left tail test, we reject if our test statistic z is less than or equal to negative of alpha over 2. Negative of alpha. Negative of z of alpha. Sorry. So this is what I'm asking. So is our test statistic less than or equal to negative z of alpha? Do we know our test statistic? Yes, we do. It's negative 2.36. Is this less than or equal to our critical value? And we know our critical value is negative 1.645. So this is negative 1.645 question mark. So is this true? Oops. Is negative 2.36 less than or equal to negative 1.645? And the answer is yes. Yes, it is. Yay. There's also another way you could visualize this. Let me just copy this image here. So we know that this is our critical region. And right here, we know that this value here, this line, is negative 1.645. And we know that our mean is 0 is there. So we want to know is z is our test statistic somewhere within our critical region. And the answer is yes. So this is our z somewhere here, because z is equal to negative 2.36, negative 2.36, which is less than, negative 1.645. So since it's within our critical region, we reject. So thus, the 3 dots just mean thus. We reject our null hypothesis, h sub 0. And again, because our test statistic z is less than or equal to our critical value, we just did a quick check. So this is true. Another way you can think about it is that our test statistics is within our critical region. So thus, we reject our null hypothesis. Great. Now, probably the most important step is that we want to interpret the result in the context of the problem. So it doesn't really matter if we know how to do all this stuff if we don't know how to interpret our result. So since we reject our null hypothesis, if you look up here, since we reject, we could say that we have sufficient evidence to conclude, and then write down whatever your alternative hypothesis is. So here, we could say that, in quotes, we have sufficient evidence to conclude that the mean, conclude that, and this is why I always write down my null and alternative hypothesis. I could literally just copy paste our alternative hypothesis, that what we wrote down, and to here. So we could say that we have sufficient evidence to conclude that the mean price of regular grade gasoline in LA is less than $4.04. So that's one way why I like to write down my my null and alternative hypothesis. So that way, when I do my conclusion, I could just copy and paste and put it right here. So this is our interpretation. We have sufficient evidence to conclude that the mean price of regular grade gasoline in LA is less than $4.04. Okay, so we just finished hypothesis testing using the critical value method. So if you go up here, right here, we just finished learning how to use the critical value method to compute hypothesis testing. Next, we're going to learn the p-value method. And they both should conclude the same result. It's just the p-value method actually tells you a little bit more information than the critical value method. Okay. So let's talk about, here we go, the p-value method. So everything what we did above was the critical value method. Now we're going to learn the p-value method. So here, the p-value method provides actually more information than the critical value method. The critical value method tells us only whether the test statistic was unusual or not. The p-value method tells us exactly how unusual the test statistic is. So what exactly is a p-value? Well, the p-value is the probability of having a data value equal to the sample statistic, x bar, under the assumption that the null hypothesis is true. So another thing you want to note here, note, the smaller the p-value, the stronger the evidence against our null hypothesis. So now we're dealing with probabilities. Another definition, a very important definition. And you actually seen this before. In the case when our population standard deviation sigma is known, the test statistic is the z-value of the sample mean, x bar. So we're still dealing with the same test statistic, z. And you're probably asking yourself, like, is this, how do we actually compute these p-values? Well, since p-values are probabilities, and we have a z-value here, which is our test statistic, do we know how to find probabilities using z-values? We do. So we actually have experience dealing with this. Okay, computing the p-value. So to calculate the p-value, use the following. So these are things you have to keep in mind. If the test is left tail, so if you're dealing with a left tail test, the p-value is the area to the left of the test statistic, z. If you're dealing with a right tail test, then your p-value is the area to the right of the test statistic z. And then if you're dealing with a two-tailed test, the p-value is just the area on the outside of the test statistic z. And one thing you want to note here is that we reject the null hypothesis if the p-value is less than or equal to the significant level alpha. So here's a way to visualize it. So let me just break this up into cases. Oops. Okay, so how do you find the p-value when you're dealing with a left tail test? And remember, the left tail test is when your alternative hypothesis, mu, is less than some value, mu some naught. So here we have the test statistic z. Your p-value is going to be the area to the left of that value here. So here in words, let me just write a couple things down. The p-value is the area to the left of z. And we already deal with areas to the left to the right of values. So this is nothing new. Okay, what happens if we're dealing with a right tail test? So your p-value is just going to be the area to the right of your test statistic z. So let me just write a couple things down. The p-value is the area to the right of z. Cool. And again, we are already familiar with finding areas to the right of z values. Finally, what if you're dealing with a two-tail test? So this is actually going to be a little bit different. So here the p-value is the sum of the area in the two tails. So here the p-value is actually the area to the left of this value plus the area to the right of this value. It's the sum of these. But the great thing about the standard normal curve is that it's symmetric. So if you find the area to one side, it's going to be equal to the area of the other side. And you just add these two values up. So now we're going to do some example of computing p-values. Okay, example 1. A test is made when our null hypothesis is mu is equal to 10 versus mu is greater than 10. The value of the test statistic z is 2.25. We want to find the p-value and interpret it. So here, I'm going to write down the test. So our null hypothesis is going to be mu is equal to 10. And our alternative hypothesis, H1, would be mu is greater than 10. And I'm going to make this in green. What test are we dealing with? Are we dealing with a left tail, a right tail, or a two-tail test? Well, since in our alternative hypothesis, we have this greater than, it kind of looks like an arrow pointing to the right. So this kind of gives you an idea that we're dealing with a right tail test. So that means that the p-value is the area to the right of our test statistic z. So so let me write this in black. Z is going to be equal to x bar minus mu naught divided by sigma over square root of n. But they already gave us the value of z, so we don't have to compute this. Again, we're just practicing how to compute p-value. So they already gave us our z, so it's 2.25. So you want to find the area to the right of this z value. Let's draw a normal curve. This has a mean of 0. So our z is somewhere here. This is our z, which is 2.25. And we want to find the area to the right of this, since we're doing a right tail test. So another way we think about this is we want to find the probability of z is greater than 2.25, which is the same as 1 minus the probability of z is less than 2.25. And we could just use the table to find out what this value is. So this is going to be equal to 1 minus 0.9876, and this is going to be equal to 0.0122. If you're not sure how I got this value, you should review how to find areas underneath curves, because we've been actually doing this for weeks now. But if you still have questions, you can always come to my office hours. Okay, so this means that our p-value is equal to 0.0122. Yay. But here we're missing a small part. We want to interpret what this p-value means. So here, in words, the p-value of 0.0122 tells us that if our null hypothesis is true, then the probability of observing a test statistic of 2.25 or more is only 0.0122, and that kind of gives you an idea whether or not it is unusual. But we'll get into that later into the notes. How about this example? We have this test where mu is equal to 5 versus our alternative hypothesis, mu is less than 5. And they already gave us the test statistic z, which is negative 0.63. We want to find and the p-value and interpret it. So here our test will be h naught, mu is equal to 5, and h1 would be mu is less than 5. Cool. And in green, are we dealing with a right tail, left tail, or two-tail test? Well, since our alternative hypothesis is that mu is less than 5, this is kind of pointing to the left. So this kind of gives you an idea that, oh, we're dealing with a left tail, oops, left tail test. So the p-value is the area to the left of our test statistic z. So to compute our test statistic, it's going to be x bar minus mu naught divided by standard deviation divided by square root of n. But since they already gave us this, we don't have to compute it. It's already given. And again, it's because we're practicing how to compute p-values. So the z is negative 0.63. And so let me just draw this real quick. So we have a standard never curve. Since it's negative, it's going to be below 0. So it's going to be somewhere here, maybe. Negative 0.63. And we're trying to find the area to the left, since we're dealing with a left tail test. We want to find this area here. In other words, we want to find p of z is less than negative 0.63, and we could use the chart to compute this. So this is going to be equal to 0.2643. And again, we already done a lot of practice of computing areas underneath the curve. We just used the table. So this, if you're still having trouble, again, I highly recommend coming to my office hours or emailing me. Okay, so that means our p-value here is equal to 0.2643. Awesome. So how do we interpret this? So we could say that the p-value of 0.2643 tells us that if our null hypothesis H0 is true, then the probability of observing a test statistic of negative 0.63 or less is 0.2643. And you notice that this probability is not so small. So it kind of gives us a hint about what does it mean either to reject or fail to reject our null hypothesis. But that's I'm going to get into that in a little bit further down the notes. Okay, last example. Here, we want to have, we have a test where mu is equal to 20 and mu is not equal to 20. And the value of our test statistic z is negative 2.70. We want to find the p-value and interpret it. So here our test sub 0 will be mu is equal to 20. And our alternative will be mu is not equal to 20. So let me write this in green. Are we dealing with a left tail, right tail, or two tail? Well, since this is our alternative hypothesis says that mu is not equal to 20, this kind of gives you an idea like, oh, we're dealing with a two tail test. Sweet. So this means that the p-value is the sum of the area in the two tails. Okay, so let's compute our test statistic is x bar minus mu naught divided by standard deviation divided by square root of n. But again, they already gave us this value. It's right here. Z is equal to negative 2.70. And again, the reason why we're doing this is because we're practicing how to find p-values. Okay, so let me just draw this real quick. So this is our mean 0. So this is saying that we want to find the we want to find the area to the left of this. And the right of the positive side. But the great thing about the standard ANOVA curve is that it's symmetric. So if you find the area to the left of this z value, it's going to be equal to the same as the area to the right of this positive z value. And all we have to do is take the sum of these two values to get the p-value. So we want to find the probability of z is less than negative 2.70. We want to find this area first because it's a lot easier. And then we could just look at our table, and then in our table it's going to be equal to 0.035. So the area here is going to be 0.035. And again, since this is symmetric, that means the area here is also going to be 0.035. So then the p-value is going to be equal to 0.035 plus another 0.035. So the p-value is going to be equal to 0.070. Cool. So let me interpret this. So we can say that the p-value of 0.070 tells us that if our null hypothesis h sub 0 is true, then the probability of observing a test statistic greater than 2.70 or less than negative 2.70 is only 0.0070. And notice that this probability is really small, and that kind of gives us a hint that it tells us something about our null hypothesis. And again, we're going to get into that in the later notes. But okay, just to review. So what we've been doing is practicing how to find p-values. So now that we have this, we could compute hypothesis testing with the p-value method. Okay, so before beginning any hypothesis testing, we have to, again, check the requirements. If all of them satisfied, then you're allowed to continue. But if only one of them does not satisfy, then you can not able to perform hypothesis testing. Okay, so first thing you want to know is that you want to obtain a simple random sample of size n. Since we're dealing in this section, we're dealing with a situation when sigma is known. We want to know the value of sigma, and then we also want to check if our sample mean distribution is normal. And this requirement can be satisfied of one or two ways: that the population is already approximately normal, or that X comes from a normal distribution, or the sample size n is greater than 30. If all this is satisfied, then you're able to perform hypothesis testing. Okay, so let's talk about performing hypothesis testing for mu when sigma is known, when we know what our population standard deviation is. In this case, we're going to use the p-value method. First step is you want to state the null and alternative hypothesis. So this step is really similar to the critical value method. You want to have a null hypothesis. So this is in the form of mu is equal to mu naught. And then you want to compute the alternative hypothesis. So this is one of three ways. Mu is less than mu naught, mu is greater than mu naught, or mu does not equal to mu naught. And again, mu naught is just number, their value. Next, we want to find the significant level, or your alpha. And then you want to compute your test statistic. And then we want to compute the p-value. And we already had a lot of practice of computing p-values. Then you want to make a decision based on that p-value. So we reject our null hypothesis if the p-value is less than or equal to our significant level, alpha. So we have to check if our p-value is less than this number, then we reject our null hypothesis. And then finally, and probably the most important thing, is we want to state our conclusion. How do we do that? Well, it's kind of similar to what we did in the critical value method. If we reject the null hypothesis, then we could say that we have sufficient evidence to conclude, and then input your alternative hypothesis here. If we fail to reject the null hypothesis, then we could say that there is not enough evidence to conclude, and then input whatever your alternative hypothesis is. And again, this is going to be different depending on what problem you're working with. Now let's do some example of hypothesis testing by using the p-value method. So here, example 1, the National Health and Nutrition Examination Survey are designed to assess the health and nutrition status of adults and children in the United States. According to a recent survey, the mean height of adult men in the United States is 69.7 inches, with a standard deviation of 3 inches. A sociologist believes that the taller men may be more likely to be promoted to position of leadership. So the mean height mu of male business executive may be greater than the mean height of the entire male population. So here, a simple random sample of 100 business executive has a mean height of 69.9 inches. Assume that the standard deviation of male executive has a height of 3. Have a standard deviation of 3. Can we conclude that the male business executive are taller on the average than the general male population with a significant level of 0.05? The first thing I want to do is actually collect all the things that I know. So probably the easiest one to look for is your sample size, your n. So here we know that they had a simple random sample of 100 male business people. So here our sample size is n equals 100. We also know that our standard deviation, population standard deviation, is 3. So here sigma is equal to 3. So in our sample here of 100 people, of 100 male business executive, they had a mean height of 69.9 inches. So since they're dealing with a sample, this is going to be your sample mean height, your sample mean. So X bar is going to be equal to 69.9. And finally, we have a significant level of 0.05. So alpha is going to be equal to 0.05. Cool. Now we want to check our requirements, like do they satisfy? Notice that our sample size n is equal to 100, which is greater than 30. So that means that that our requirement is satisfied. So we're all good. Next, we want to state the null and alternative hypothesis. So here we want to know our h sub 0. So that's going to be mu is equal to some value, and our alternative hypothesis, which is h sub 1. And this is going to be mu is less than, greater, or not equal to some value. We have to figure this out. So looking back at our problem, we had this sociologist. He believes that taller men may be more likely to be promoted to position of leadership. So he's saying that the mean height mu of male business executive may be greater than the mean height of the entire male population. So we know that the entire male population is 69.7 inches. So this is saying that he's saying that mu is greater than 69.7. He's saying that male executive are taller than the mean average of the whole male population. And then, so that means our null hypothesis is that mu is equal to 69.7. So let me write this in green. Since this is greater than, are we dealing with a left tail, right tail, or two tail test? Well, since this is greater than, and here's a little trick. If this kind of looks like an arrow that's pointing to the right, so this kind of tells you that we're dealing with a right tail test. Cool. Also, I'd like to actually write down what our null and alternative hypothesis is saying. So here, our null hypothesis says that the mean height of male executives is 69.7 inches, because 69.7 inches is the average male height population. But this sociologist saying that no, the mean height of male executives is greater than 69.7 inches. So this is our null and alternative hypothesis and what they're saying. Okay, now we're going to do some analysis. We want to find the value of our test statistic. So this is going to be z is equal to x bar minus mu naught divided by sigma divided by square root of n. So we know all these values. We know x bar, which is 69.9. We know sigma, which is 3. We know our population size, our sample size, n, which is 100. And we know mu naught. And this is just the value in our testing. Here is going to be 69.7. So all we have to do is plug in our values. This is going to be equal to 69.9 minus 69.7 divided by 3 over square root of 100. And if you put this in your calculator, you should get 0.6666, but you could round this to 2 decimal places because that's how we find areas under curves, which is 0.67. Okay, now we want to find the p-value. Since this is a right tail test, we need to find the area to the right of our test statistic. In other words, let me just draw this real fast. We want to find the area to the right of 0.67, and this is our mean 0. You want to find this area. So let me just write this down. Since this is a right tail test, our p-value is the area to the right of our test statistic z. Cool. So this is asking what is the probability of z is it's greater than 0.67, which is equal to 1 minus the probability of z is less than 0.67. And again, you could use the table to find this value here. So this should be equal to 1 minus 0.7486, which is equal to 0.2514. So our p-value is equal to 0.2514. Oops. Let me just box this. Nice. So what is the conclusion? Now, how do we know when to reject or fail to reject our null hypothesis? Well, if you look at our step here, if the p-value is less than or equal to the significant level alpha, then we reject our null hypothesis. So here we want to ask a question. So question, this is a Q. Is our p-value less than or equal to our significant level alpha? Question mark. So what is our p-value? 0.2514. Is 0.2514 less than or equal to our significant level? And here, alpha, our significant level is 0.05. So this is less than 0.05. So is 2.2514 less than 0.05? Question mark. And of course the answer is no. No, it is not. So our p-value is actually greater than our significant level, because 0.2514 is greater than 0.05. So that means thus, the 3 dots just means thus, we fail to reject our null hypothesis, H0. Awesome. Now for the last part. We want to interpret our result. So it doesn't really matter if all this computation is correct. If we don't know how to interpret what we're computing, then there's not really much of a point. So this is actually a really important step. Since we failed to reject our null hypothesis, we could say that there is not enough evidence to conclude, and then write down what our alternative hypothesis was saying. So here, we could write that there is not enough evidence to conclude that, and then what was our alternative hypothesis? This was our alternative hypothesis right here. So we could literally just copy and paste this statement into the last section here. So we could say that there's not enough evidence to conclude that the mean height of male executives is greater than 69.7 inches. So next, I want to do one last example, but this time in a case where we have to deal with a two-tailed test. And the reason why is because typically, in this case, a two-tailed test is a little bit more challenging, only because we have to consider taking the sum of areas. So here, at a large company, the attitudes of workers are regularly measured with a standardized test. The score on the test range from 0 to 100, with high score indicating greater satisfaction with their jobs. The mean score overall of the company's employee was 74. So here, the mean score overall the company's employee was 74, with a standard deviation of 8. Some time ago, the company adopted a policy of telecommuting. Under this policy, workers could spend 1 day per week working from home. After the policy has been in place for some time, a random sample of 80 workers was given the test to determine whether their mean level of satisfaction had changed since the policy was put into effect. The sample mean was 76. Assume that the standard deviation is 8. Can we conclude that the mean level of satisfaction is different since the policy change, with a significant level of 0.05? So here, again, I want to kind of gather all the information that we have. Probably the easiest one is to determine our sample size. So here we know that we have a random sample of 80 workers. So N is going to be equal to 80. Next, we also know that our sample mean was 76. So here, X bar is going to be 76. Oops. 76. And then we have a standard deviation of 8. So here, sigma is equal to 8. And we're dealing with a significant level of 0.05. So alpha here is equal to 0.05. So notice that our sample size n, which is equal to 80, this is greater than 30. So that means that our sample mean distribution is approximately normal. So that checks one of the requirements. We also know that we have a simple random sample, and our population standard deviation is known. So we're good to go. Next, we want to state the null and alternative hypothesis. So here, our null hypothesis, h is 0, this is going to be mu. It's going to be equal to some number. And our alternative hypothesis is going to be mu. It's going to be less than, greater than, or not equal to some number. So notice in the problem, so we have to read the problem really carefully. So here, it's saying that, can we conclude that the mean level of satisfaction is different? Is different since the policy change. And before the policy change, they had a mean score of satisfaction of 74. So this is asking that, can we conclude that it's different? So it's not asking if it's greater than or less than 74. It's just saying that if it's different. So that kind of gives you an idea like, oh, we just have to say that it's not equal to 76. Sorry, 74. 74. Sorry, yeah, because before the policy change, it was 74. So this is asking if, can we conclude that the mean level of satisfaction is different from 74? So here, our alternative hypothesis is mu is not equal to 74, and our null hypothesis will be mu is equal to 74. Okay, and so let me make this green. So what are we dealing with? Are we dealing with a left tail, left tail, right tail, or two-tail test? Well, since our alternative hypothesis says that mu is not equal to 74, this gives you an idea that, oh, we're dealing with a two-tail test. Nice. So what is our null and alternative hypothesis saying? So here, our null hypothesis is saying that the mean score satisfaction is 74. But the alternative hypothesis is just saying that it could be different. So we could say that the mean score satisfaction is 74. Oh, sorry. It's different. Or it's different from 74. So we don't know if it's greater than, less than the 74. It's just saying that it's going to be different than 74. The mean score satisfaction is going to be a different number. That's all that's stating. So now that we have the null and alternative hypothesis, we could compute the value of our test statistic, our z. So here z is going to be equal to x bar minus mu naught divided by sigma over square root of n. Since we know all these values, we could just plug them in and then just get our test statistic. So this is going to be equal to 76 minus 74 divided by 8 over square root of 80. And this is going to be equal to 2.2361. But again, we want to round to 2 decimal places. So this is going to be equal to 2.24. So just to make it clear, z here is 2.24. There we go. Okay. Now we want to find the p-value. So what does this mean? Since we're dealing with a two-tail test, so this will be z. This will be the negative of z. So it's asking, we want to find the area to the left of the negative version of our test statistic, and we want to find the area to the right of the positive version of our test statistics, and take the sum of these areas. But the great thing about the standard normal curve, so this is the mean 0, is that if we find the area of 1, let's say we find the area of this, since it's symmetric, it's going to be exactly the same as the area to the right of this z value. So let's find the area here because it'll be a little bit easier. So here would be P of z is less than negative 2.24. And the reason why it's negative is because it's below 0. So we need to have the negative version of our test statistic. So this is going to be equal to, if you look at the table, is 0.0125. So this means that the area here is going to be equal to 0.0125. But since this is symmetric, the area here is also going to be 0.0125. So that means our p-value is going to be equal to 0.0125 plus 0.0125. So it's going to be equal to 0.025. So just to make it clear, our p-value is equal to 0.025. And let me just box this in. Awesome. Now we want to state our conclusion. So we want to know what this means. Do we reject or fail to reject our null hypothesis? And for that, we need to ask a question. Is our p-value less than or equal to our significant level alpha? Question mark. That's the question we want to ask. So is our p-value, which we just computed, is 0.025? Is this less than or equal to 0.05? Question mark. And the answer is yes. Yeah. So we know that 0.025 is definitely less than 0.05 because this is a smaller number. So let me just write this in words. Since the p-value is equal to 0.025 is less than our significant level alpha, which is 0.05, we reject our null hypothesis. So just to make it clear, thus we reject H naught, our null hypothesis. That's our conclusion. And the last step is probably the most important step. We want to interpret our result. So it doesn't matter if we did all this, if we don't actually know what it's saying in the end. So since we reject our H naught or our null hypothesis, if you look back in our notes, if we reject the null hypothesis, we could say that we have sufficient evidence to conclude and then write down our alternative hypothesis. So we could write that we have sufficient evidence to conclude, and then what you could do is just copy paste the alternative hypothesis. So we could say that we have sufficient evidence to conclude that the mean score satisfaction is different from 74.